Nathan, thank you for getting that posted. Pause just a second. Make sure that you can go ahead and get started right in time. All right, I think it looks like we're pretty good here. So Nathan, our next speaker here is going to be Nathan Noma from the University of Minnesota Twin Cities, and he's going to talk about verification of EKF attitude data with computer vision.
Yes, hello. So yeah, that was the introduction. That's the title of my research. This was a research project over summer 2020 that I completed in conjunction with the UMN UAV lab. So there's a little bit of background for this research project. I'm a senior in aerospace engineering at the University of Minnesota. This internship or research experience was initially supposed to be an internship at NASA Ames, but that was canceled due to COVID, obviously. So this was a last-minute research project thought up by Professor Flotten and supervised by Curtis Olson of the UMN UAV lab to still give me a valuable research experience this summer. So I'm very grateful for that. And after my 10-week tenure was done over the summer, I believe the work was continued by another U of N student named Isaiah Wardlaw and Kurt. So there has been some development since I've worked on it, since I last worked on it in August. But this, I'll just be going over the work that I did this summer. So some background for why this is important. Robust and reliable attitude data, or otherwise known as roll pitch yaw, is important to have for accurate reporting of UAV states during flight. It's essentially when you have an aircraft, it's just of the utmost importance to have a good idea of what its behavior is and what to expect it to do when doing certain maneuvers, especially with automatically generated flight missions. And so we wanted to find a way to verify or further improve current control technologies to make sure that the avionics were as robust as possible. In this case, the UAV that we used had data reported by an extended Kalman filter, which is essentially, it just is a filter that takes data from the accelerometer, IMUs, gyroscopes, and GPS, applies initial conditions and expected variances in the data reporting from those sensors, and returns attitude, positional, and velocity data. One issue with this is that it's subject to error, whether it's calibration or bias error or random error from the large number of data points. And there's also no way to directly validate this, as it feeds back into the flight computer. It's a feedback loop, and so it can't be directly validated by an outside observer when you're flying through the air. So the goal of this project was essentially to develop an algorithm to validate and improve this attitude reporting data provided by this filter using image data. So basically, we would mount a camera on the UAV and use the information provided by this video and images to essentially extract roll and pitch data and compare it to the EKF filter to essentially compare these and use the video as a sort of truth reference frame and see how well our EKF was reporting. So you can see it in these images here. That left image is what was provided from the video. You see some lensing effects and other things, and then basically we would process this image and detect the horizon line and extract data from that detection. Some challenges associated with this project. The data is visual and not quantified like the EKF data, so it's provided in a different way. So we'd have to do the processing ourselves to try and find a way to accurately compare these, since it's not reported in the same method. There's a difference in sampling rates between the videos and the EKF. So essentially the video is, I think, captured in 30 FPS. The EKF reports in a couple hundred hertz, so there's a huge sampling rate difference. So it's not like the data is being reported at the exact same time. And so there is some interpolation that was needed. Overall, it's worked out fairly well, but it is a difference between the two data sets. The camera might not be aligned with the accelerometer and GPS axes because of the way it was mounted. I got this video from Kurt due to COVID restrictions. I wasn't able to go out and fly but I just received this from a previous flight that he had conducted. Um, and so, like I said, I wasn't able to see how the camera was mounted, but some differences might arise if they were not all calibrated together. And inconsistency in mounting the camera angle between flights. If the camera angle changes between flights, it's harder to compare the data between flight sets and kind of get a better idea of how it performs from flight to flight. There's processing challenges. All of this data was processed post-flight, but ideally we'd be able to take this algorithm and use it to verify the EKF data in real time to improve the accuracy of an autopilot. There's limited effectiveness in adverse conditions as it's taken from video data. So if there's a camera glare, and there's everything is blotted out by the sun, it's pretty hard to get a decent idea of what the landscape is looking like. Luckily, we're in Minnesota, and the example that we used was on a flat terrain, so it was able to detect an accurate horizon line, which was generally corresponded to a roll angle of 0. So it might not work as well on mountainous or hilly terrain, depending on the slope. And also, there's like poor lighting, variety of other issues that could arise that make it difficult to take good images in any other application. And obviously, like I mentioned, COVID restrictions prevented me from working in person with this technology. So an overview of the procedure that we used. I'm going to be walking through the procedure that we developed for our algorithm. Essentially, we would take the video, as you saw earlier. The image was subject to a lensing effect, like a fish lens effect, just due to the shape of the camera. So we'd have to take that image, undistort it so that we wouldn't have that curved horizon, so it'd be straight. Separate the color channels. Luckily, we had a blue sky, so we were able to extract separate color channels. I'll go into that a little bit in further detail later. Basically convert it to grayscale and binarize the image. Run edge detection to detect where the horizon could possibly be. Run a Huff transform on it to detect likely candidates for large linear segments in the image. Select the best candidate for the horizon line and extract the roll and pitch data from that. So first, basically, to take the image and remove the fish lens effect, we would just need a matrix of camera values and lens distortion factors that are dependent on its geometry. This was all provided by Kurt. Like I said, I wasn't able to gain access to the camera, so thankfully I already had known all this information from previous work. You basically just apply a matrix transformation to the image as it's loaded in, and it returns this image. So you see the one on the right has a relatively flat horizon, as what you would expect if you were observing from that angle. And I forgot to mention, all of this processing was done in MATLAB with the image processing and computer vision toolbox. So for the procedure, and then further, we'd select the blue color channel and convert it to grayscale. Like I said, we had a clear sky, so the blue color channel had very intense blue values on the top part of the image, and so it was a pretty obvious distinction between where the sky started and ended, and then generally on the ground there wasn't a large cluster of blue values like there would be for a clear sky. So that provided an easy way to filter out a general trend for where the horizon could be. We'd binarize the image with the Otsu method, which is a built-in algorithm in MATLAB, in the MATLAB function, which essentially just goes through the image and finds the likely, it compares the contrast values between all the pixels and binarizes the image as such. Like I said, more intense blue values on the top means that it would kind of default to a 1 state in the binary image, and the darker foreground where it's gray and brown hues would default to 0. So you can see that image on the left is the binarized image that I was working with. Then we would run canny edge detection, which essentially just looks at the binary image and detects the boundaries between the dark and light regions in the image. So you see on the right, You can tell a pretty obvious horizon line because of that straight line that runs the entire width of the image. And then we would run the Hoflines algorithm. This essentially took that canny edge detection image and found the longest line segments in there. We were able to filter out a lot of unlikely candidates from that by tuning the sensitivity and setting like a minimum line length. So obviously the horizon line would be the longest one. So generally we'd filter out the smallest detections. And through trial and error, we found that generally the longest line segment yielded the horizon line. There were some inconsistencies that I'll get to in my results here. And so we'd find the horizon angle directly from that endpoints. The Hoflines transformation would provide endpoint data, so you'd be able to do basic trigonometry and extract the roll angle from that image. And then we would find the pitch angle through vector operations. So you'd establish a normal vector pointing out from the camera in the center of the image, and then draw a vector to the horizon line that you detected, and essentially just find the angle between those. And we were able to find the pitch angle with that. And then we could draw it back onto the image as shown below. So you see that this, at least for this frame, it yielded a very good general idea of where the horizon was. For the results, overall, the video data matched the EKF well. It detected the horizon accurately for the most part. There were differences in sampling rates, so anyway, also, the video was about 4 minutes long, but the EKF data spanned the entire flight, so it required me to kind of work with the data and try and line it up so that it was looking at the same segment of the flight. So there were some difficulties with matching that. There was occasional false detections due to other lines in the image, such as if you were flying at a high roll angle and there's a large field. If there's like a distinction between the field and then a patch of forest or something, that would tend to be the longest line in the image, so there was some false detections there. And like I said, there's pitch offset due to the camera mounting angle, so that had to be kind of figured out just by inspection of the data, since we didn't know exactly what the mounting angle was. So you see here, the top figure was what we found for the roll values. You can see there's spikes and noise in the data due to those false detections. So I kind of had to filter those out manually. That's a place where future work was oriented, I believe. But you can see it matched the EKF data very well for the most part, and kind of is used. It shows potential for it to be used as a truth reference for the EKF data. For the pitch values, you can see from the top image there was that offset due to the camera mounting angle, so that's what I needed to adjust for in the filtered values. Similarly, there was noise, but overall, pretty close trends, so it shows potential to use as a comparison. As far as future work, the processing took a long time. It was like a 4-minute video at a fairly high resolution, so it needs to be optimized to run in real time for attitude control. Like I said, this was all done post-processing, so if this can be streamlined to work in real time, that would be better. It needs to be further optimized to minimize those false detections and spikes like I showed earlier. I think that was the work continued by Isaiah and Kurt, but like I said, I had limited time working on this, so I'm not quite sure where they ended up with that. Overall, just have a repeatable procedure for mounting the camera so it's valid between flights. And then we could also use yaw estimation by tracking features in each frame, but we never got to that. We were focused more on the roll and pitch. And as far as acknowledgements, thank you, Professor Flotten, for helping set this up. Thank you, Kurt, for providing supervision on this project. Thank you, Isaiah, for continuing to work on this project after my tenure was over. And that is all I have, so any questions?
Yes, quick questions. We have 1:43, so we have time for about one question.
So this is clearly an aeronautics project. NASA does aeronautics. Do you see space applications for what you've done here?
I believe there's potential. It's a little bit more difficult to do in a space application as it's not as much of a grounded reference frame as when you're using planes. Like obviously in space, orientation of the aircraft is much more difficult to obtain because you don't have a horizon to reference the aircraft or the spacecraft attitude to. So I think there's potential to expand it to a space application. But I don't think you could probably use this algorithm in the same way. I think there is potential for using a variety of sensors to kind of, maybe even visual data to kind of help orient a spacecraft, but it's much more difficult when the horizon or objects are much more distant. You could maybe use star tracking or something. If you could, identify where the spacecraft is and use locations of stars that you know. It's possible, but obviously it's much more complicated than using just a horizon line as a reference frame.
Great.
Great.
Let's
Thank you.
virtually thank our speaker.